Right, okay, so this is the last vid in the thermo and heat and gases and all that jazz section. It's about ideal gases and the gas laws. So, first thing, to know all the gas laws relating pressure, volume and temperature, to know the assumptions of an ideal gas, to know the ideal gas law itself, and to know how to relate molecular speed and temperature. So the first gas law is Boyle's law, and it states that the pressure of a fixed mass of gas at constant temperature is inversely proportional to its volume V. So P is proportional to 1 over V. So we can state that PV equals a constant, and that we can say if the gas goes through some expansion from one state to another state without a change in temp, then P1V1 equals P2V2, where P1 and V1 is its pressure and volume at one state, and P2 and V2 is its pressure and volume at another state. Now, that should be constant. You can do it P3, V3, etc. and so on, and that's Boyle's law. Right, it looks like this, with P against V giving this inverse curve, like you can see. And these different lines represent different temperature, with increasing temperature going up there like that. If you plot P against 1 over V, you get these linear lines with increasing temperature going that way. Now we call these isothermals because they are uniform temperature along those lines, so there are isothermals. Okay, the next one is Charles' law, which states that the volume V of a fixed mass of gas at constant pressure is directly proportional to its absolute temperature, T, which is measured in Kelvin. V is proportional to T, V over T is a constant, so if that gas goes through some change of state, sorry, no, that's the wrong thing, so it goes from one state to another state without a change in pressure, then V1 over T1 equals V2 over T2. Da, 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 da. And yes, Charles's law looks like that. Charles's law was used to define absolute zero, as I'm sure I've said before in a previous vid. With pressure, where's my mouse? There you are. Pressure. Which is larger pressure? Larger pressure. We'll talk about that in lesson actually. Larger pressure would mean slower changes in volume. No, I mean large. I think with larger pressure to smaller pressure, but I'm guessing there. I think I need to check that out. You need to check it out. Homework. There you go. The last of the three gas laws, even though it's not the last of them, but the last of the three gas laws is the pressure law, or Gay-Lussac's law, which states that the pressure of a fixed mass of gas at constant volume is directly proportional to its absolute Kelvin temperature, T. The P is proportional to T, so P over T is a constant, and then if it goes through some state change, not a state change, I said state change again, you know what I mean, goes from one state to another, and P1 over T1 is equal to P2 over T2. Happy. And so different gases will behave differently, but ultimately they're all linear relationships. Boom. Also, it would give you the same minus 272.15 at zero pressure, because only in a zero volume state can you get zero pressure, even though it seems weird because you said the inversely proportional. Oh, anyway, that's true. Right, okay, so ideal gas. So an ideal gas is the sort of idealized gas. It allows us to understand the macroscopic or bulk properties of a system such as pressure, volume and temperature. And we use the kinetic theory model to set our conditions for an ideal gas, and the assumptions of that model are the following. So there's a large number of molecules all in rapid and random motion. We know what that means. Random, it means unpredictable. So it's important that we can't see patterns in the way they move. 2. Particles, or atoms or molecules, occupy negligible volume compared to the volume of gas, aka if you were to vary the volume significantly, it wouldn't result in like being stuck by hitting into those particles. That's obvious, I suppose. All collisions are perfectly elastic, which is not true, but it's an assumption from the model. Time of the collision is negligible compared to the time between collisions. Negligible forces between particles except during collision. Right? So there are the assumptions for the kinetic theory and the ideal gas. Some related stuff that most chemists will be well aware of. So the Avogadro constant is the number of atoms in 12 grams of carbon 12, and Na is the number of atoms per mole of gas, which is 6.02 times 10 to the 23 of them. Molarity in moles is the number of moles contained in a substance. The molar mass is either measured in kilograms per mole or more commonly in grams per mole. It is the mass per mole of a substance. So mass of oxygen gas 0.032 kilograms per mole or 32 grams per mole. I don't know why that's there. I'll put it there. I feel bad about it now. Okay, so to calculate the number of moles, N in mass M of gas of molar mass Nm. So we relate the number of moles, the molar mass and mass with that formula there. So the number of moles is equal to the mass in grams over the molar mass. To calculate the number of molecules in N moles, we simply times the number of moles by Na, or we times M over Mn by Na, which is the same. So cool. Have a little scan of those and check that you understand them. Okay, so our ideal gas equation then. An ideal gas is one which obeys the gas laws and subject to the assumptions of the kinetic theory of gases. So for an ideal gas, PV is a constant at constant temp, V over T is a constant at constant pressure, and P over T is a constant at constant volume. It follows then that PV over T should be a constant for a gas that is not changing a great deal. But yeah, it is. PV over T is a constant for one gas, that you don't reduce the number of molecules present or change anything physical about it. You change its pressure and its volume and its temperature, and they'd be related like that. Okay. So if PV over T is a constant, the magnitude of that constant depends on the mass of the gas being considered. So for 1 mole of gas, that constant is the universal molar gas constant, which is 8.31 joules per mole per Kelvin. So for 1 mole of gas, PV over T equals R. So PV equals RT. And for N moles of gas, we can say PV equals nRT, which I'm sure if you've done chemistry you'll be well familiar with. So pressure in pascals, volume in meters cubed, N is number of moles, R is gas constant, and T is temperature in Kelvin. Absolute temperature. It's important that you don't use degrees Celsius here, because unlike other scales, it doesn't have the same zero. So the ideal gas equation can also be expressed in terms of the Boltzmann constant, which is the gas constant per molecule. So K equals R over Na, and K, the Boltzmann constant, has the value 1.38 times 10 to the minus 23 joules per kilogram. And since K equals R over Na, then R equals K Na. And we can do some rearranging now. We can put that into PV equals nRT to get PV equals NK NAT. And since Na equals the number of moles times the number of molecules of a gas per mole, which equals the number of molecules in the gas, we can say that PV equals NKT, which is another way of putting it, particularly useful if you've got things in terms of number of molecules rather than in terms of number of moles. Now we have the combined gas equation, which says that for N moles of gas of volume V1 at pressure P1 and temperature T1, we can say that P1 V1 over T1 equals NR. And for the same amount of gas whose volume has changed or a new pressure or temperature, we can say that P2 V2 over T2 is still equal to NR. Right? So we can combine them and come up with that, just like we did for all the other 3 gas laws. So PV over T is a constant for a gas, and it will stay a constant as long as you don't let gas leak out of it. So there's a question for you. Do it and bring it in to the next lesson. Have a little pause of the vid now. Right, okay, speed of gas molecules. So the speed of molecules within a body in thermal equilibrium varies according to the Boltzmann distribution. When I mean in thermal equilibrium, I mean the entire system is all the same temperature. So I'll stick a thermometer into any part of the system at any direction, it would be that temperature. It's in thermal equilibrium with itself. What you can see is, where's it gone? So you can see that at 300 Kelvin, the distribution, so this is the number of particles as a proportion of the total that are doing that speed. So we can see that there's none are doing none, and a very few are doing a really small speed. The majority are doing about this speed, and then as you get higher and higher speeds, there's a smaller and smaller proportion of particles doing those higher speeds. Increasing the temperature shifts this average speed up a bit, but it also reduces the number of particles that have actually done it and broadens out the Boltzmann curve. It happens again. Now you've got a higher average speed, but now more particles doing a much broader span. Less particles doing that speed, or a smaller proportion of particles doing that speed. So we say that few molecules have either very low or very high speeds, and none have zero speeds. Distribution of gas molecular speed depends on temperature, and as the gas temperature increases, it becomes flatter and broader, as we just said. Higher the temperature, the greater the proportion of high-speed molecules, and the smaller the proportion of low-speed molecules. Right, fantastic. Molecular kinetic energy and temperature. So we know that the mean speed is the average value of the speeds of all the molecules, right? That's pretty easy to get your head around. And since the mean speed, C, with a little hat, I've forgotten the little hat, of the molecules in a gas increases with temperature, the mean translational kinetic energy of the molecules also must increase with temperature. When I say mean translational kinetic energy, I just mean the average kinetic energy. It's called translational for a reason that I'll tell you in a bit. Well, when you get into lesson, actually, it's a derivation, which is hell. Yes, so we can state this. The mean translational kinetic energy of a molecule of an ideal gas is directly proportional to the absolute temperature of the gas. Now, we'll cover a derivation for that in a lesson because it's just a bit too complicated to go over in a vid. Right, so we know that that's true, and so we can say that is true, which is, obviously, I will derive that. I promise it's not just jumped out of nowhere. So E equals 3 over 2 kT. So you can see that 3 over 2 k is just a constant, and that E is directly proportional to T. So the average kinetic energy of any particular gas molecule is solely dependent on the temperature of the gas, not any other traits of the gas whatsoever. Now that makes sense because we know that temperature is a measure of kinetic energy. But here's more proof that it is. And where K is a Boltzmann constant. And so given that an axiom for an ideal gas is that all of its internal energy is the sum of all the random kinetic energies of the particles within a body, we can say that the total internal energy is equal to 3 over 2 n kT, where n is the total number of particles in that system. Right, so if you've got 300 grams of helium-4, and it's at internal thermal equilibrium at a temperature of 400 Kelvin, what's its mean translational kinetic energy, which is just that equation, and what is its total internal energy, which is that equation at the bottom there. All you'll need is those two constants, so I'm pointing there, those two constants, and you'll need your n equals m over m thing. But anyway, you should be able to work it out. Right, excellent. That was a short vid for my standards anyway. That's ideal gases and thermal speeds, molecular speeds and temperature. Right, bye.